Welcome to the AbsInt webinar for release 18.4. My name is Christian Humbert, and today I'd like to show you the latest features of our binary level analyzers, StackAnalyzer, aiT, TimeWeaver, and TimingProfiler. Let's start with the section about the new aiT annotations. And here I'd like to firstly introduce the value partitioning. So, to motivate the value partitioning, please consider the following small example program. Here I would like to assume that the mode variable, which is checked in these 3 consecutive if statements, that this one is a global variable and that its content is unknown to the static analyzer. So what would happen in the static analysis is, for instance in the timing analysis, that if the mode variable is unknown, which is equivalent to consider a value range of min-int to max-int, that the analyzer would consider the first if statement to be true, so the condition, and would call the f function, the second one where mode equals 2, and will enter the g function, and the third one as well, that where mode variable equals the value 3, and we call the routine h. So that would mean that the WCAT in total for this small program would be equivalent to the summation of the WCAT for the routine f, g, and h, which is of course a highly overestimated WCAT. So in order to improve that WCAT result, we would like to introduce in this release the so-called value partitioning. And value partitioning enables now the value analysis to introduce one separate analysis context for each value of a variable that is possible. And a variable on binary level means registers or memory cells. So in this small example, we could, for instance, formulate the following value partitioning annotation. We start at some routine point, the partitioning, and say that we would like to restrict the memory content or the values for the variable mode with the 3 values 1, 2, or 3, and no value else. The consequence will be that the analyzer will analyze this small program in 3 different contexts. The first context, where mode variable equals the value 1. The second context, where it equals 2. And in the third context, where the mode variable, the content equals 3. So that at the end, the WCAT of that small program will correspond to no longer to the summation of the 3 timings of the routine f, g, and h, but this time the maximum over the WCATs for each function, which would be the desired behavior, of course. So in this small example, I decided that routine g becomes the WCAT, the maximum over 3. So now let's see that directly in the tool in a small demo. Let's have a look to this demo 1 here. This is an aiT WCAT analysis. I'm starting that, and well, there is an unresolved computed call problem here, but let's for now have first look to the program flow. So the routine looks like this. We have here some global variable p, which is some non-volatile but global variable, and where the analyzer doesn't know anything about its content. And there is a first if statement which checks if p equals 0. If that is the case, then we enter the then case where we assign another variable f, which is a function pointer variable, with some message handler from table entry 0. Then there is another check here afterwards where we check if p equals 1, and we assign a different message handler in that case, and so on. We can also have a look to the source code. Maybe it's a bit more convenient to see the structure. So there are consecutive if statements here. And of course, logically, all these cases are mutually exclusive. But if the analyzer doesn't know anything about P, if the content is unknown, well, it will, as you can see here in the worst case, consider that we have to enter the then case here, execute that code, then we have to enter here, execute it, and so on. So all of them, all of these then cases are lying on the worst case path, which is of course a bit overestimated. You also see that here in the control flow graph. So the red path indicates the worst case, and we go through all of them. Of course, what you could do now is you can preload the content of P. You can say, well, P has a certain content. Yeah. So let's try that one here in the annotation file. You could say, for instance, area P contains data. We say 1. Then we restart the analysis, and you will see that in this case only the case for P equals 1 will be feasible, all others will become infeasible. But this is of course restricting the analysis domain a lot, because you predefine the value of P. You would much more be interested in what is the worst case content or the content of P leading to the overall worst case, right? And so this is not a good option. What you can do is, in fact, using trace partitioning so far, because you have here control flow joins at every if statement here. So here's a control flow join. Let me just start it again to have the original situation. You have here control flow join from the case that P was equals 0 or not, and here for P equals 1 and so on. At all of these basic blocks, you have control flow joins, and what you could do is you could span trace partitioning. You can start a trace partitioning at every of these basic blocks where you have more than one incoming edge. I've prepared that one, and by these annotations here. Of course, you have to use offsets then to each of these basic blocks, and you say begin partitioning trace. So this will already solve our problem, but it's not really convenient because these, on the one side, the offset addresses might change if you recompile later. And another disadvantage of that concept is that whenever you split the contexts here, the control flow join, you introduce, you double your existing context. So up to here, we just had one context for this routine. Then we say, well, we have here control flow join. I'd like to start a partitioning here. So I double my context information. So if I go to show value analysis results, I see from that point on, I have two contexts. Next point here, I'd like to split again because I have a control flow join. So I double my existing context again as well. So from that point on, I have four contexts, and so on up till to the last block, the fourth block. So if I go to show value analysis results, I now have 2 to the power of 4 contexts, namely 16 actually for that basic block. So your your number of contexts exponentially grows, of course, by the structure here. This is also a disadvantage. So what you actually would like to have here is really distinguishing the different cases for this P variable. And this is now possible using value partitioning. okay, by distinguishing the different values for one variable. Let me show you how this is actually working. So if I start the analysis again, I have the original situation. And if I introduce a value partitioning annotation, which looks like this, right from the analysis start, I'd like to start partitioning over 4 different cases, namely that the variable p has the value 0, 1, 2, or 3. And this will lead to the fact that the analyzer will analyze that routine main ifs 4 times, and namely for the context p equals 0, p equals 1, p equals 2, and p equals 3. And it will find the worst case of these 4 contexts, namely the one if p equals 3, then we are having this message handler, the 4th handler for the function pointer variable f, and this will lead to the global worst case execution time. And the function pointer will, of course, then also be resolved, because in each context we have one defined message handler, and we collect them all in order to resolve that computed call. Next topic is the automatic generation of the call target annotations from the DWARF view. Let's have a look to some other example. So this reuses the demo program from before. So our main ifs function, and you remember we had this unresolved computed call. Let me show you that in the source code file as well. So here was the program point where we have the computed call, which is unresolved in the analysis, and this was because we had these 4 different if statements, and the function pointer variable f was assigned with 4 different values, namely 4 different message handlers. And let's assume for this demo now that the value analyzer is not able to resolve the computed call automatically, because we do not have the value partitioning or trace partitioning activated. So in this case, if the value analyzer is not able to resolve the computed call, the user has to resolve a computed call by annotating the call targets, or in this case by extracting the call targets from some constant table. And what we see here is that this f variable is assigned by different message handlers that are extracted from some message handler array. And the structure is coming from this. Here we have this message variable, and it consists of some handler array here with 4 entries and some integer value. And we are interested in this handler component. So what we could do now is we could generate here a template for this unresolved computed call. Let's do it via add annotation. The template suggests to annotate the target routines as a list, but we can do better by extracting the components, target routines, from this handler array. And to do so, we can switch now to the DWARF debug view. And here's our message variable. If we unfold it, we see the structure of it. It consists of the handler array, which has 4 elements, and the content. And we are interested in this handler array, right? What we can do now is to do a right mouse click on that component and say copy ai's calls annotation to clipboard. If we come back to our annotation file, we can paste the corresponding annotation suggestion here in our ai's file. And what we are actually interested in is this last calls component here. This was now automatically generated in the ai's syntax to address that handler component. and the user does not have any longer to derive that AIS expression, that complex area expression, by your own. And if we now redo the analysis, the computed call will be automatically resolved using that annotation, namely that we extract all message handler from that message.handler array. In release 18.4, we introduced the so-called Trace-Iterative Decoding concept. This is a new way to resolve computed calls by extracting the target information, the routine target information, from the program flow traces. This feature will initially be available in the TimeWeaver analyzer, but can also be provided for StackAnalyzer as well. Let's have a look to the tool chain and the analyzer structure. You know that we always start with decoding the executable program or the tasks that we are analyzing. So we reconstruct the call and control flow graph first. And here the challenge is to resolve dynamic computed calls. And in the past, we provided a feature which was called ValueAnalyzer Decoding. That means it's the play together between the value analyzer and the decoder. That means as soon as the value analyzer detects potential addresses, target routines, it reports them back to start the decoding process over again in order to have a complete call and control flow graph. Now we are introducing another back edge from the Trace-Analyzer in TimeWeaver, because in the trace data, in the program flow trace, we actually see which functions have been executed, have been called at the dynamic function pointer call. And if your trace coverage is complete, then of course this resolution of the computed call targets will also be complete. If this is not the case, you will get of course trace coverage information back. You can extend call targets, of course, still by the AIS file, and you can combine them with the automatically extracted routines from the Trace-Iterative Decoding. Let's have a look on a small demo. So here we have a small TimeWeaver analysis, demo 3, and we analyze task 0. We have here some trace file, some program flow traces of type Lauterbach Nexus. And we start the analysis and see a lot of unresolved computed call warnings here. So there is some routine sequence 1, which has, I think, 5 computed calls, sequence 2, another 5, and sequence 5 has 3 computed calls. The ValueAnalyzer Decoding does not work here because there's simply not enough information about the initialization data of these node arrays, which are used to extract the call target informations. So I can go here to one of them, say show in file, and we see here inside of sequence 1 we have here from node array the 10th element shall be used to call the function here, and so on. So all of them are unresolved and cannot be resolved statically by using traditional concepts like ValueAnalyzer Decoding. What you now can do, since this is a TimeWeaver analysis which extracts program flow information from the trace data, you can go to Setup, Decoding, and enable the Trace-Iterative Decoding, which is by default activated in new projects. If I restart the analysis now, and by the way, the call graph looked like this, lots of unresolved computed calls. If I restart the analysis now, well, these computed call targets, as you can see them, in the first round they are still unresolved. Then we have the Trace-Analyzer, and this one will start or will communicate the trace targets to the decoder and starts the decoding process again. And this time all computed calls are resolved automatically by extracting the target information from the program flows trace data. So you see, there is no unresolved computed call left, and we are able to compute the worst case execution time estimate based on that information. The user, of course, has to check if the extracted call targets are complete. If there are functions missing, you can, of course, add them by providing traditional call target annotations. Next topic are the improvements or changes in the graphical user interface. And I'd like directly switch to some example here. So the first change in the graphical user interface is the statistics about the timing contributions. If I start here some timing analysis, for instance, so in this case it's a TimeWeaver, but it's similar for TimingProfiler and aiT. If I go to the statistics, I have this WCAT estimate or WCAT view, and we do no longer show the self and cumulative contribution in machine cycles if there was a clock rate annotation provided. You can nevertheless configure that and do right mouse click on the column overview and activate the self cycles or cumulative cycles information here again if you're interested in that. All right, next improvement in the graphic user interface is the analysis queue. You can stop already scheduled items in the analysis queue or add new again. So for that, have a look here to our analysis project. We have 4 analyses here in this APX project. I start them all, but now I realize, oh well, maybe I'm not interested in analysis demo 5 again and demo 6, so let's stop them again from the queue. And then I see, oh well, okay, let me have this start 6 again introduced into my analysis queue. So I can dynamically switch off or add analysis items to the analysis queue again. Another improvement is the interactive abort feature of the iterative decoding process. So here in this example, in this demo, we have this trace-iterative decoding, and let's start it. So we see that we have this computed call targets that were extracted by the program flow trace information. But assume this process of iterative decoding can take a lot of time, and you can iterate several times. What if you want to see how the call and control flow graph looks like after a certain iteration step? You can stop now this iterative decoding process. And I'd like to show you how you do that. Let me start it and directly stop after the first value analysis step. You do so by directly clicking on stop, holding it, and click on stopping that iterative decoding. And you see what happens? Well, now we stopped, of course, after this value analysis, the first round, and display the call and control flow graph, which is, of course, incomplete in this case. But it allows you to debug some analysis problems, and you do not have to wait until this iteration has finished. So the last point in the GUI section is that from release 18.4 on, we do no longer support loading target settings from a machine settings file. So we discontinue that direct loading from machine settings file. What you have to do in order to continue using your existing analysis projects, you would have to first import that machine settings file into your existing APX project file. You do that by switching here to specify manually, clicking on the import machine settings button, and selecting that machine settings file, which was referenced here in the loading section. By importing it, all configurations here in the MSF file will be done in the project configuration here, and you have to do that in the release 17.10, because this option here, loading it from machine settings file, is no longer available in 18.4. But if you import it once in the older version 17.10, you can save now your project file here, demo new, and reload it in 18.4. And you see your settings are still there, but this time saved in the APX project file. Last but not least, let's talk about some more TimeWeaver specific improvements. And I'm switching here to the tool. We now support more trace formats, and what you see here, of course, our internal trace format, Traval. Then we have a new support for the Infineon tab format, which comes from out of the DRS-MTB tool. We support 3 different formats of the Lauterbach debugger, the ASCII export format, the binary flow format, and the Nexus BHM raw data format. We also support the PLS debugger with the tab format that we can export from the Universal Debug Engine, and the CSV format from the iSystem WinIDEA debugger. Then we have some improvements here in the statistics view of the TimeWeaver analysis. Let's analyze this small example here again and go to the statistics. There is the trace segment overview, which shows the timing for each trace segment. So the minima timing, the maxima, the average observed timings, and the timing which were effectively used for the worst case computation at the end. Typically this corresponds to the maxima if there is no filter applied. What you directly can see here on the first view is that these segments are now named in the call string style, so you directly see the context from where you come from. Yeah? So you enter at some address, you call the routine node 0, and at this address you call the sequencer 2. And for that snippet, in this calling context, you get the timing overview. There is another new feature here. For instance, if I double click here on that segment, I'm interested in this data here. You can export now the raw data to CSV for post-process that timing information for the selected segment. And in the graph overview, you also have some more information at timing nodes. For instance, if I go here in that routine, this is the timing node. If I do say right mouse click here, show node, I also see timing information for each context. In this case, it's a bit boring. Let's go to some routine where we have more context. For instance, here at least 2. And there's at the end, I guess, some timing node with timing data. This one, say show node. and you see we have 3 contexts here. The first, at this address we entered routine sec1, and at this address we called node 0. We have a different address for node 0 for this block here, and a third one, and they have different timing contributions. So you can see that in this timing information view here by clicking right mouse click on this timing node and say show node. All right, this concludes my demo about the features of TimeWeaver. And so I'm at the end of my presentation about the latest features in 18.4. If you would like to have more information about this current release, please feel free to go to our website, www.absint.com, release notes. Thank you very much for your interest. Bye-bye.